Okay, cool. Yeah, so I've been I haven't had much chance to I was gonna say do a lot of cars. I did a couple, like two or three passages, not a lot, but I've been trying to switch to more doing content diagnostic stuff and
Yeah.
just reviewing that. And that's what I've been doing. And yeah, I look a couple questions on that. And hopefully, I mean, we're supposed to meet on Friday. I was hoping, is there any chance that we can meet later that day or no?
Let's see. Uh, no, I have people from 4 to basically 8, which is what when I work until.
Okay, that's fine then, whatever. Okay. Yeah, so I just have a couple questions on this
Yep.
like this CP stuff. Yeah, so I'm just gonna keep going. I have some notes and I'm just gonna keep going to the next question and next question. But yeah, I remember reviewing this question and I understand kind of have an idea why it's A because a lot of the strong bases like LiOH and BaOH, all of them are from there or like in group 1A. But I don't know. I don't understand the other. I don't really understand the other three answer choices on why they're wrong.
Okay. So, yeah, so this is just something that you just have to know. So the
Okay.
group, yeah, they like sodium, lithium, etc. They form um hydroxide when you put them in water.
Right, like LiOH2 and BaOH2, like the strong bases or something, or
Wait, say that again?
like Li, like the strong bases. Is that what it's saying?
So, tell me what those examples were that you said. L
Like, well, I don't know if it's in group I. Wait, let me see. Let me see. Here. Is it lithium? No, it's like these, right? Like NaOH2 or KOH2 or RbOH2. Like,
Wait,
aren't they like the strong bases or something?
you're thinking of like NaOH with one O
Yeah.
because you know, this will give you positive one cations. So you're thinking of NaOH and stuff, not OH2.
Oh, right. Yes. Right.
But
Yes.
those are the bases. But what this is saying is that if you just take those, if you take like lithium or sodium or something like that, and you put it in water, it'll cause the water to turn into hydroxides.
Okay. Okay. And then why the other three? I kind of just guessed on this. I don't know why the other three answer choices are
Uh,
wrong, I guess. So what do
yeah,
how do
so
you yeah.
so for B, it says insoluble salts. And that's not the case. They are very soluble. Um, like sodium, lithium, all that stuff. And then react with nitrogen to form hydrides. That doesn't happen. Um, because a hydride is a negatively charged hydrogen. And then also D to produce nitrides. That also isn't something that it would do. So this is just something to know.
Okay. All right. I guess I'll try to make a card or something out of it.
Hmm.
Let me see which one. 613. Okay. Yeah. These I kind of got the idea because I know like well when I reviewed it, right, because it said PO43 minus. And I completely disregarded the three there.
Yep.
But yeah, like I guess I wanted to just go over like I guess in this case, yeah, ions. Like what are some common ions you think that I should probably know?
Oh yeah. Yeah, like the polyatomic ions that
Yeah,
so like phosphate definitely have to know, and I would say even know how to draw it.
like H3 PO4
You're thinking
minus and then H2 PO4 minus like that stuff or
so you're thinking of the acid, but I mean just the ion itself. Do you know what that would look like? The
or phosphate?
yeah.
Yeah, that would just be PO4 3 minus, right?
Yeah, but I mean like do you know how to draw it?
Oh, Damn, it's been a while, so probably not, to be honest. No.
So yeah, you want to know how to draw it.
Okay.
So let me show you. So it's P double bonded to oxygen, single bonded to oxygen with a negative charge, single bonded to oxygen with a negative charge, single bonded to oxygen with a negative charge. This is important to know because you're going to see that it, for like a kinase, you have uh, a phosphate that you're taking from like ATP to give to something else or vice versa. So a lot of times you'll see that this comes up like when you have a hydroxyl group and you do a nucleophilic attack. So, you know, it's going to be an electrophile that you'll see.
Like in like in ATP hydrolysis, is that what you're referring to? Kind of?
Yeah, so that would be breaking it apart into the inorganic phosphate ion like this.
Okay.
Yep.
Sounds good. And then like any other ions besides that, or like is there any specifics besides that you think? Or like should I mean I know there's like the miles down sheet that I've been trying to see like the ions, but like there's so many.
Oh,
So it's like
really?
which one I should
How
prioritize.
many?
Actually, wait, I mean I think I might be exaggerating. Let me see. Where's it? Let's keep going. Where are the ions? Where are you? Where are you? Where are you? Yeah, there seemed like a lot here, I guess. I mean, I kind of understood like eight. If it has eight at
Okay.
the end, it typically means more oxygens, and if it's eight, there's less oxygens. So I kind of saw
Oh,
the trends, but
okay. So this is important to know. So basically, so when you have oxy polyatomic ions, the number of oxygens, the larger the higher the number of oxygens, the more it'll turn. So like for like if you have three oxygens here, it's the ite. If it's four oxygens, it's the eight. And then for the nitrites and nitrates, it's the same thing. But what would, this be called?
I don't think it would be sulf. I don't know, hydrogen sulfite,
Well, it's a type of it's acid. So
sulfuric acid.
so if it was H2SO4, it would be sulfuric acid.
Okay.
So basically, if the acid form ends in ic, the salt or ion form ends in ate.
Hmm.
And if the salt or ion form ends in, oops, ite, the acid form will end in OUS.
Oh, so that should be sulfurous acid then.
This one, right?
Yeah, the top one, SO3.
Yep. And then what about this?
Okay, so yeah, so that's nitrite. So that should be a nitrous acid, I guess.
Yep.
Nitrous
Yep.
acid.
Yep.
Okay.
And then you
Got
can see for the P's that the ITE, so like for the chloric ones, we have four possibilities. So in the middle, it'll be like ite and ate, as you would expect. But if it's less oxygens than the ite, it'll be with the prefix hypo, which in general means less. And
hmm
then here is going to be per, which really comes from hyper meaning more.
Okay.
Yeah. So, and then you have so you also want to know like what the carbonic acid looks like. It's H2CO3. and it
Mm.
can turn into the bicarbonate ion HCO3 minus, which
Hydrate.
can then turn into the um, carbon carbonate ion.
Mm. Okay.
Yeah, and then ferric, same kind of principle with the ic and the us, except this time it's related to charge. So larger the charge, the more it'll be ic. And then your negatively charged ions will be ending in IDE. And hydride here is your negatively charged hydrogen. So, oh yeah, and then they talk about it here as well.
Oh, yeah, I didn't see that.
Yeah. Do you want
Okay,
to
yeah, I can
extend?
screenshot it, I guess. I guess I have the information here. Okay, I guess I'll go over it again then.
Yeah, yeah. See, yeah, looks like a pretty cool cheat sheet.
Yeah, they don't have these cards in his sheet, but in his deck, but I guess I'll add them. Okay. Let's see what else we got. Oh, I'm gonna go get my charger real quick. One
Yep.
second. Okay. 20. Ah, yes. So yeah, in this question, essentially saying it's a strong acid and sold for household use as muriatic acid. And then what are the concentrations of hydronium and hydroxide ions? And I knew it was like we could use like 10 to the negative. Well, they gave us a pH. I kind
So,
of okay, so I could do negative pH.
so check this out.
Okay.
So I'm going to show you, because I always want to show you, more than one way to answer your question. Now, this is a strong acid, they said, right? Right?
Oh, could you say that again? Sorry, I was kind of getting closer
Oh
to
yeah. So, I always want to give you more than one way to get your answer. So I'm going to give you two ways. First way is they say it's a strong acid, right?
Yes.
So what should be higher? Hydronium concentration or hydroxide concentration?
Hydronium.
Okay. Which choice has that?
Oh, yeah, I guess D.
All of these show a lower amount of hydronium compared to hydroxide, right?
Yeah.
So that's one way.
Okay.
The other way, the actual like mathematic way. So if you go from, so yeah, if you go from, so okay, the pH of something is going to be negative log of the hydronium concentration, right?
Yes.
Now, to go the, so that's if you have pH and you're trying to find hydronium. Um, sorry, that's if you have hydronium concentration, but you're trying to find pH.
Yeah.
Now, if you have pH and you're trying to find hydronium concentration, you just do like the inverse of a log, which is just an exponent. So uh, your H plus concentration, it will be 10 to the negative pH. So in this case, it would be 10 to the negative 2.3.
Yeah. But then how did they get like the like really thing is like how did they get the five in this thing here? That was
So now if we start with so like the 5e negative 3. Um, so a shortcut, because you're going to do the net. So like this is the hydronium concentration. And if we want to convert that into a pH, we would do the negative log of this, right?
okay. The negative log of the concentration, yes.
Yeah. So now I'll just show you a shortcut. So you take the exponent value and you flip the sign. So we're going to get 3. And you subtract it by the log of this number. Okay.
Okay.
Now, what's log of 1?
0.
What's log of 10?
1.
So anything between 1 and 10, we can estimate or approximate as zero point 0.5.
Sure.
So now this will be 3 minus zero point 0.5, which will give you 2.5, which is pretty similar to our 2.3 value.
Oh, okay. That makes more sense. I see what they're doing. Okay.
Mhm.
Gotcha. All right. Let me see.
Why don't you do it for this? What's the pOH of that?
So that would be 12 minus log of 2.
Okay.
So that'd be like maybe 11.8, somewhere around there.
Well, you could just estimate it to be
12.
oh no, so log of anything between 1 and 10, you can just approximate that to be zero point 0.5.
Oh, so it's not like it's close. So it wouldn't be like 0.2, 0.3. It's just you're just saying it's just gonna
Well,
be in the range of 0.5.
they would be different values. I used to have students memorize like log of 2, log of 3, log of 5, log of 7. Um,
Okay.
because with those logs you can figure out all the other logs, but I realized that um they never ask anything to that level of precision. So
Okay.
we could just treat everything as like being log of any log between 1 and 10 is just zero point 0.5.
Okay. So I guess yeah. So in this case it would be 12 minus 0.5. So that'd be like what, 11.5, I guess.
Yep.
Okay. All right, so is there any besides like I guess I'll try to remember this log 1 between 10 and 0.5. Do you know any other like numbers that I probably should try to just know? Maybe
So
since we're on that.
how would you say you are for the MCAT math stuff?
Uh, I think in the recent couple of weeks, like doing like chats prep and stuff, like I feel like I've gotten a little better, but not as much. Like if like for example, if they give me because like I know there's a lot of times you gotta estimate. Like sometimes I have to kind of like multiply each individual number sometimes. So it takes me a bit of time. I don't think I'm like
Okay.
that great.
So I guess we'll see as we like move forward with these, but I have a lot of really good math tricks. Like I kind of realize that I do math in a way that's very different from how a lot of people do math. Um, Meaning like a lot of times I like to use fractions because that way things cancel out and you don't have to round. Um, so but okay, but yeah, I'll show you that stuff, if we, as we see them.
Okay. Let's see. Electrolytic cells, yeah. Okay. So it's been a little bit of time. I just wanted to like confirm with you, like at least like electrolytic cells and like the concept behind it. So I really understand from it and how it's different from a uh voltaic cell is just because how the reaction is just non-spontaneous, and then we just have a then we have a so it needs a voltage source.
So check,
So it
so check this out, right? So remember when I said when you were plugging in your laptop, it was an electrolytic cell.
yes.
So let me describe it in that way. So because could be kind of hard to kind of like conceptualize because like electrochemical cell they have like the two beakers and stuff and we're like how often do we see that, right? But what an electrochemical cell is, and that's by the way the same thing as a voltaic cell, same thing as a galvanic cell, same thing as a concentration cell. So it's basically like a battery,
Okay.
meaning you're converting chemical energy into electrical energy. So
Yes.
I'm gonna draw it as a battery like this, and let's say that so like a regular lithium ion battery is going to have a higher amount of lithium ions, let's say at this top part, plus charge there, and at the bottom a small amount, so negative charge. And if I connected a wire, current carrying wire between these, you'll see electrons travel from the negative end to the positive end, okay?
Yes.
Now, that's as the battery runs. Now, this happens until equilibrium is established, which means that enough electrons have reached the positive end to give it a charge of zero, and enough electrons have left the negative end to give it a charge of zero. And this is when you have a dead battery. Okay.
Okay.
So what do you do with the dead battery? Well, you can charge it. So what you can do is you can plug it in to an outlet, some external source of electrical energy. You could also plug it into a battery. And now this is going to force the reaction to take to run backwards, meaning momentarily the anode or yeah, this bottom end here is going to have a positive charge and this top part a negative charge. And that's
Right.
just because these electrons that come in, you want to have come in on the at the anode down here to recreate that charge separation, which allows it to turn back into that battery. So,
Okay.
and oh, and then this is your electrolytic cell,
Okay.
right?
So see, but like in the context of an electrochemical cell though, so you could say that the external voltage source is what's driving that oxidation to happen compared to a voltaic where it's like just happening by itself.
Say what you said again.
That the external voltage source in the electrochemical cell is
Well,
essentially
elect
driving.
electrochemical cell is the same thing as a voltaic cell, which is the same thing as a galvanic cell, which is the same thing as a concentration cell.
Okay, so everyone's just thinking based
Electrolytic
of.
is a different one.
Okay. Well, yeah, so like in an electrolytic cell, in this case, then like that battery itself is like driving the oxidation and happening it. It's like it's making that happen.
Uh, where? So which of these examples are you talking about?
Not specifically this, but like when I look at an example with like the electrodes and like the
Yeah, yeah.
battery up there.
Uh-huh.
So like that battery, those electrons, like it's pulling that, it's making that oxidation reaction like on the anode happen, essentially, right?
Are you saying, tell me that again? Like I understand what you're saying, but
Mm.
are you saying that the what's the first all right, so what's so okay, so in electrochemical, galvanic, etc., you're converting chemical energy into electrical energy. So the redox reaction is what drives the electricity.
Okay.
So you get a conversion of chemical energy into electrical energy.
Okay. Like,
Okay.
and the same thing's happening in electrolytic. The same thing is happening. It's still chemical is being converted into
Nope, nope.
electrical, right?
It's the so see if you could open up the shared PDFs folder. I have a one in there that yeah.
So annoying. Yep. Where do
Go
you want me to
to PDFs
go? Okay.
and it'll be called Electrochemistry.
Electrochemistry, galvanic? No? Oh, there you go.
Okay, so you could press this plus button on the bottom to zoom in a bit. All right, so here we go. So this is the thing they were talking about. So over here I wrote galvanic cell, also known as electrochemical. What we do is we take advantage of the natural difference in reduction potentials of two different metals to spontaneously generate an electric current. So here on the left, we have this left beaker with a strip of zinc. On the right, we have another beaker with a strip of copper. And these over here are the reduction half reactions. So we see that for the zinc, it has a reduction potential of negative 0.76.
Mm-hmm.
For the copper, we see a reduction potential of 0.34. Now, what happens in an electrochemical cell is that whichever has the higher reduction potential is the one that will be reduced. Okay.
Okay.
And whatever has the smaller reduction potential will be oxidized.
Right.
So between zinc and copper, which one would get reduced?
Cop.
Copper.
Copper.
Okay.
Yep.
Now that means the zinc must be oxidized, which means that this reaction, instead of it going that way, it would go this way.
Mm-hmm.
And that also means that your oxidation potential is you just take your reduction potential and you flip the sign. So
Right.
now it becomes positive 0.76, right?
Yes.
So, oh, I wrote it down here. So zinc solid turns into this. And you can see that electrons, so the zinc gets oxidized, which means it loses electrons. That's why the electrons are traveling through this wire from zinc to the copper. Okay.
Okay.
So here I wrote for the electrochemical cell, the E cell potential is always positive. It's always greater than zero. And your cathode is negative. Sorry, cathode is positive. Anode is negative. And electrons travel from the thing with a low reduction potential to the thing with the high. And then the salt bridge just completes the circuit. But that's for the galvanic cell. Any questions here?
Okay. Yeah, no, that's fine. That's good.
All right, let's scroll down. So now, oh, go up a little bit. So this, so this should be a negative over here. Like the reduction potential of something will be equal to the negative of the oxidation potential. And your cell potential is the sum of the reduction potential and oxidation potential. Um, that you might see written as like cathode potential minus anode potential or something like that,
Yeah.
which is fine. Uh, I just think it's more intuitive to just to do it this way. But you'll
I
get
agree.
the right answer. Um, and oh, and then our delta G is equal to NF cell potential, or sorry, negative NF cell potential. So that means that if in order to be spontaneous, what sign must cell potential have?
Positive.
Exactly. So, all right, awesome. So then I wrote, eventually all of the electrons will reach the cathode and all the cations will reach the anode. This is equilibrium, in other words, a dead battery. So we can scroll down. Remember, a battery is an electrochemical cell which turns chemical energy into electrical energy. So to charge the dead battery, you plug it in to an electrical source using electrical energy to convert into chemical energy. This is called an electrolytic cell. So now you actually have the thing with the high reduction potential get oxidized, aka give its electrons to the thing with a low reduction potential. And
Yep.
your cathode is now negative, anode is positive, and your cell potential is negative, which, again, means it's not spontaneous.
Yep.
All right, we can scroll down. Oh, and then I wrote it's a galvanic cell in reverse.
Mm.
Yeah. And now these are examples. So there's already the recharging battery example that I showed you,
Yeah.
but you can have electroplating. So say that we want to plate an aluminum pair of sunglasses with gold, right?
Mm.
We have the aluminum reduction half reaction here and the gold half reaction here. Now, which one would be reduced here?
The aluminum, right?
Yeah, why?
Because it's in the cathode, right? So that's going to be reduced.
Oh, let's say we didn't have that.
Well, I mean, technically, right? You said that we need to plate an aluminum
So,
sunglass.
so basically what I'm getting at is that for electrochemical, whichever has the higher reduction potential gets reduced. For electrolytic, whichever has the lower reduction potential gets reduced. And so
Okay.
the aluminum is a negative, which means it'll get reduced for the electrolytic cell. And the one with the higher one, so the gold here, we want this to be oxidized, so it releases gold ions. So we reverse this to get that, and then you end up with your negative cell potential here.
Makes sense.
Yep,
Could you could you go over that one more time? Why exactly is like let's say that was a good thing that you pointed out. Like let's say this picture didn't exist for me then.
yep.
Like how exactly is the E cell again? Why is that negative again?
I don't know.
Why is it
So
negative? Or
what?
not why is it negative? Or like why do we determine for electrolytic cells to use that as the the the, the reduction potential, I guess, or the cathode or whatever.
Yep. Just because you want the electrochemical like cell to run in reverse, you want to force it to run in reverse.
Okay.
hmm
Okay. That makes sense. Okay.
So, and yeah, and then this is the last example. So, say you're in a submarine underwater, how do you breathe oxygen? They use electrolysis, that's where the name comes from, electrolytic cell, to make oxygen from water. So there's this external source here, which is the battery, and we have, a cathode, an anode, and essentially we're just splitting the water into O2 and H2, and we just put those in different, like, containers. So, yep.
Okay.
So the key difference here is that
It's running in reverse, basically. Right?
uh-huh. And yeah, it's like yeah, forced that way. And then yeah, this is where we get the free energy uh
Okay.
relationship. Mhm.
Cool. All right. We'll check it out later again, but I kind of get it
Yep.
now. Okay. What's the next question? Let me see. It's 2050. Okay. Um, why is this is D? I kind of didn't really understand what the
So imagine you had something like that, like, and you tried, so like, let's see. I'm trying to look for something near me, but basically, like, if you had this, it would topple over, right?
Mhm.
So, okay, so the center of mass is where that gravity, you know, force comes down on, right?
Sure. Okay.
So A, B, and C, the center of mass has, a base. Whereas for
Mm.
D, center of mass doesn't have a base. The base is to the right of it. So this is going to produce like a torque, like, and this is going to just tip over.
Mm. Okay. That makes sense. Right. Um, yeah, I got this. Yeah, so in this question, the biggest thing I was thinking about, so what I did was like I got it wrong and then I went over like Bernoulli's equation. And then I tried to input Bernoulli's equation, but I'm like, the only way to get the answer is I would have to put the dynamic pressure as zero. But I don't know if that's like
So check this out.
the thing to do.
So Bernoulli is applying conservation of energy to fluid dynamics, meaning fluids that are moving. Okay. This is, we don't have any moving fluids here. So this is going to be the gauge pressure, um, which is this.
Okay. Is it a
Now,
minus or it's plus or
uh-huh.
does it matter, the sign limitation or no?
So this is the official formula, but you'll see what we do with the sign in a bit. But
Okay.
typically, this equation is used for things that are submerged. So let's say I had like a container of water and I just had a ball floating on top. It's experiencing an atmospheric pressure, right?
Yes.
Okay. Now let's say this ball is submerged here. It still experiences the atmospheric pressure, but it also experiences the pressure of the water on top of it, which we can write as rho gh,
Hmm.
right?
Yeah.
Okay. So that's the typical example. Now, for this question, let's start off with this conceptually. Now, let's say pressure on the left, pressure on the right. If these two levels were equal, what can you tell me about the pressure on the left and pressure on the right?
Yeah, so they're both exerting the same pressure, right?
Yep. So they're equal, right? Pressure left equals pressure right.
Okay.
All right, now what about this?
Yeah, so here the balloon is exerting more pressure than the atmospheric pressure of the air.
So
So P to the
pressure,
right is greater than P to the left.
good. Now for this example,
Yeah, so here it's P to the left is greater than P to the right.
good. So, and now I'm going to give it, you some multiple ways. So, okay. They're telling us in the question stem that the left side is open to the atmosphere,
Hmm.
and that the atmospheric pressure is 1 E5 pascals, right?
Yep.
Now, how many kilopascals is that?
I think that is 10 to the, let's get so 10 to the, should be 1 times 10 to the 2
Yep.
kilopascal.
So 100, right?
Yeah. Oh, that makes
So we
sense.
could say 100 kilopascals is atmospheric pressure, right?
Hmm.
All right. Now, since the pressure on the left is higher and the pressure on the left has that atmospheric pressure,
Yeah.
the pressure on the right must be smaller than atmospheric pressure, right?
Yeah, that makes sense.
So we can get rid of these, right?
Okay.
All right. Now it's a question of this, meaning that the difference between the pressures, like the pressure on the left, pressure on the right, is by this amount, meaning pressure on the left is equal to pressure on the right plus rho g h. So we could write it like
Hmm.
this. We
Okay.
could we could also write it like this. Well, yeah, we could write it like this because this shows that pressure on the left is is equal to the pressure on the right plus that column, the rho GH column.
Okay.
Okay.
That
So
makes sense.
that's just so we know that pressure on the left is higher than pressure on the right, but by how much? That's going to be the rho GH.
Okay.
Okay. Now we have to solve for pressure on the right, right?
Yes.
So then what can we do from here?
Yeah, we already know the pressure on the left, which is 100 kilopascal. So, and then we can just subtract the density times gravity times height.
Okay. Now we can have our 1 E5 pascals minus, so I'm going to write it over here for more room. So the rho is 14,000 kilograms per cubic meter times G. What are we using for G?
10 newtons per kilogram.
Now, is this the first time you've seen G with those units?
Yeah, I don't see it that much. I usually just see it as what, meters per second squared, I guess.
Yep. So,
That's it, I guess.
so, um, so if F is equal to ma, and let's say A is G, so F is equal to mg. If you solve for G, you would get force over mass, right?
Oh,
Should
right.
be the Newton over kilograms. Now, the what this is the so okay. If we think about universal law of gravitation, right? Mass one, mass two over r squared, right?
Yeah.
And this is between 2 point masses like this, right?
Hmm.
Let's say that mass one is the mass of the Earth and radius is the radius of the Earth. And then let's say that we take this portion here and we zoom in like to the level where we're on the surface of the Earth, where appears flat. We experience a uniform gravitational field here. And so if you end up plugging in the values for G, big G, mass of the Earth, radius of the Earth, you get 10, meaning G. That's how we get that number.
Mm. Interesting. I didn't know that. Okay.
Yep, yep. So you could think of this as so in order for something to be affected by gravity, it needs a mass, right?
Hmm.
So the 10 newtons per kilogram means that an object will experience 10 newtons of force on Earth's uniform gravitational field per kilogram that that object weighs.
Mm. Okay.
Okay?
Makes sense.
Yep. So for this, we can write 10, newtons per kilogram. And then for the height, what can we write?
Yeah, so since we already have this in meters, the density, I would probably convert that into meters. So that's like half
Well,
meter.
we still need to add height though. Rho GH.
Yeah,
Like,
right. So this is rho and this is G,
yep.
and the H would just be 0.5 meters, right?
Okay, yeah, yeah, yeah. So I can just turn that into 1/2,
Yeah.
and that goes into this 7,000 times, right?
Yep.
And that times 10 gives you
70,000.
70,000, right?
Yep.
Okay, so let's see. So here we have 1 E5 pascals. Oh, sorry. And then what's the unit of this 70,000?
Yeah, so just be newtons over meters cubed, so that's Pascal.
Uh, I should have added this. This is meters.
So yeah, so that'd be meters. Yeah, my bad. So meters squared, right? Because that would cancel out. So just have meters squared.
Good. All right, and now we just have to take this value and subtract it from 1 E5 pascals,
Mm-hmm.
right? So it'll probably be even easier to put it into kilopascals. So like 1 E5. Oh yeah,
That's
I
just
already
one.
asked you.
Yeah,
Yep.
okay.
So this would be the 100 kilopascals minus how many kilopascals is this?
70, right? 70. One,
Yep.
two, three. Yeah, 70 kilopascal.
So you would
30
get 30
kilopascal.
then, right?
Okay.
So
Okay.
so there it is. So basically, so first we were able to eliminate A and B, right? And then we thought about it conceptually with the drawings on the left. And then, eventually we ended up using a formula, but the thing is, like the biggest gripe that I have with like pre-med physics is that they teach it in such a way that, you know, you're holding the calculator and you're reading the question and you're just plugging and chugging. And
Yeah.
on the MCAT, and that means like you don't even really think about it. You just think, all right, I'm going to put it in an equation. On the MCAT, it's not ever going to be like just a simple application of a formula like that. It's going to require, you know, um, it's going to require like critical thinking and, the ability to conceptualize, visualize things, and then think about perhaps the relevant formula, but also how to use that formula because you see that we ended up doing this, right?
Yeah, we didn't add it like that.
Exactly, because guess what? If you added it, you would have gotten this.
Yeah,
100 plus the 70, right?
yeah.
Now, what about this one? What do you think could have happened here?
Probably because they might have
Yep.
an extra 0.7 or something. Something with a 70,000. I don't know what they would have done, but
Yeah, that would be if you had 100 minus 7 rather
yeah.
than 70, right?
Hmm.
So, so yeah, I
Okay.
always want you to have more than one way to approach a problem and then when it comes to but yeah, it's all dependent on having that like kind of like foundational conceptual understanding before you do anything with formulas. So,
Okay.
and then
So you're
also,
saying,
yeah, and also just, you could see how other people do with these like percentages. Um, and it should make sense, right?
yeah.
Like there should like still be some logic to the other choices and stuff.
Okay. Yeah, last question too, like back to that though, because you said
Yep.
this was a static fluid. Well, can't we
Oh
assume that
yeah.
if it's moving down, right, wouldn't that be considered technically the fluid's moving, right? So it's not really static, right? No?
Well, it's giving us this the way it is, right?
Oh, you're right.
Right?
Yeah, okay. That's a good point.
So, hmm
Okay. Yeah, because I guess I thought I'd assume like that, but that makes sense. Okay. Let's see what else we got. 61. What's 61? Yeah, this was something about the ratios, and I
yeah, don't worry
I
about this one because this one, there's nothing in the question stem that indicates whether we're using Pascal's law or Bernoulli. So don't don't worry about this one.
okay. Um okay, yeah, I guess we can go over this question. Yeah, I guess we can go over this question. Yep.
So now this invites the topic of magnetism.
Mhm.
How are you with that?
I watched a video. I understand it a bit more, but maybe we can kind of like silly drill it today.
So what is it? What is magnetism?
What is a magnet? I guess from what I understand, magnet is essentially a if you have a moving charge and
Hmm.
that's perpendicular,
Huh?
as long as it's perpendicular, it can exert a force and that, well, yeah, as long as it's moving as perpendicularly, I always forget to the field, I guess, that you get a magnetic force, I guess. That's what I kind of understand.
So yeah. So and the thing about it is that it's in 3 dimensions. So let's say that I have um well, okay, so a moving charge will create a magnetic field. It will also be subject to a magnetic field. And let's see. Um, and now so in 3 dimensions, so like let's say this is the velocity of the charged particle,
Okay.
perpendicular to that will be your magnetic field, and then perpendicular to both will be your magnetic force.
Yeah.
That's so the entire point of the right hand rule is to be able to do this in 3 dimensions.
Hmm.
And also the point of the sine term, so like for, you know, magnetic force, it's Q V B sine theta. The sine just means it's just like torque, torque has sign in it to mean that you want it to be 90 degrees.
Hmm.
So if the charge velocity is perpendicular to the capital B, which is a magnetic field, it'll it'll be the sign term will just be one, right?
If it's 90, yeah.
Okay, so now let's think about, let's say that we have a I always forget like the into page, out of page thing. Okay, into page is the X.
Yeah, circle's out of page, right? Think so.
So let's say that we have, a charged particle enter this region of being into the page.
Okay.
What so I want you to tell me what direction so it'll experience a magnetic force. I want you to tell me what.
Should be to the left, right? It's no, to the right, to the right, to the right. Think
Uh
so, right?
this way, right?
Yeah, to the right.
And that means also that it would start moving in this direction, right?
Yep.
So okay. So now once it's here and it's moving here, what's the magnetic force?
Should be up.
So this is now going to move this way, right?
Yep.
So, let's say we're here and this is moving up,
Should be to the left now, right? That's going from there. Yeah.
and then that way, right?
Yeah.
And then here.
Yeah, so if it's going down, that should go down, I think.
Okay. So, any pattern here?
Yeah, so it's moving in a circle, right?
Exactly. So, that means that we can take this formula and set it equal to your angular or centripetal force,
Mm, okay.
which is mv squared over r,
That makes sense.
right?
Yeah, because I remember I was reading that and like I saw like when I was reading the answer choice, it said that like how I can equal both of them. But
Yes.
now it makes sense because the fact is moving to a circle, that's the reason why we can like equal it to the centripetal force. That makes sense.
Yep, yep. So they're asking about what changes to the magnetic field strength and the velocity would produce a decrease in the radius of the particle's circular trajectory. So, um, what's the proportionality between, you know, like these values and the radius?
Yeah, they seem to be inversely relationship, right?
Oh, you said inverse?
Yeah, so as you increase the magnetic field, the radius decreases, I guess.
So, all
Okay.
right, let's try this. Let's solve for radius. So I'll write this again. So QVB, it's going to be perpendicular, so I'm not writing the sign. And then we can say that that's equal to
Sure.
mv squared over r. So let's uh let's
All
solve
right.
for,
Just for, yeah, because we gotta solve for magnetic field, right? So that'd be B
or you know
E.
what? We could actually just divide both sides by v to get this, right?
So you get MV over QR.
over just R.
What about the no Q?
Oh, sorry. So yeah, I initially said to solve for R, but we don't actually have to do that because here I can just see that I can cross out the V. So I see that um the relationship between the um magnetic field and the radius is an inverse
Mm,
relationship, right?
yeah.
So a decrease in the radius would be caused by an increase in the magnetic field strength, right?
Decrease in radius. Yep. Yep,
Good.
correct.
And now the velocity is the numerator here.
Mm,
So the radius and the um, velocity are should be um, directly proportional.
yep.
It might be hard to see because it's in a fraction.
No, I see it. The B and the V, yeah, that makes sense. Because if I put two and then I multiply that by two, right, your magnetic field will probably multiply by two as well. So I get that.
Yeah, yeah. I'll just do it like this. So this would be MV over QB. Yeah, this is better. So yeah, this shows that radius is proportional to velocity and inversely proportional to magnetic field strength. So if you want a decrease in the radius, you want a decrease in your velocity and an increase in your magnetic field strength.
Mm, okay.
Mhm.
Cool. All right. Is that the extent of magnets, or do you think there was anything else I should probably like kind of know? That's what I kind of also understood, but I don't know if there's anything else. Yep.
What related to this topic?
Yeah, to magnets. Do you think there's anything else besides like these things, or no?
Oh yeah, there's there's a lot of things. So like well, yeah, there's one other main thing that I can show you like, so this should handle most of it,
Okay.
but I'll see how you do with the rest of the questions. But
Okay.
yeah, there's gonna be one like yeah, so
Understood these. 16. Oh yeah, this I didn't know this, but why do we have to do this part? The V squared or the V22 minus V1 squared. So this
yeah.
is when we're finding potential energy, is it change in voltage or is it just V squared? Because I
Very
just put in five, I think I put in four squared. Yeah, I put in four squared when I calculated it first
yeah.
time.
So that's a very, very good question because so first of all, the potential energy in a capacitor and the potential energy, like elastic potential energy in like a spring,
Okay.
both look like the formulas for kinetic energy, right?
Yeah.
Like
Yeah.
one half mv squared, one half cv squared, one half kx squared.
Yeah. Yeah, I
Okay.
didn't really notice it till now, but yeah, you're right. Yeah.
Yep. Now, when it comes to the one for the spring, that's when it'll be a delta x value. One
Yeah,
half,
have kx, yeah, delta x squared.
yes. But for the other, for the capacitor one, it's just your voltage. Okay. Which means that if so that means that we're going to have to solve for potential energy at one voltage and then potential energy at another voltage, and then we subtract the two.
Gotcha. That makes sense. Okay. So again, it's only for elastic potential energy where we're doing a change in X. But besides that, it's
Yep.
fixed. It's fixed. Okay.
So we can have 1/2 CV 2 squared. Like I'm going to say this is V2
Okay.
minus 1/2 CV1 squared, right?
Hmm.
Now we can factor out the 1/2 C part, right?
Yeah.
And then we can have V2 squared minus V1 squared.
Mm.
So that's how they got this over here.
Mm. Okay. I see. That makes sense.
Yeah. And yep, and then we can do our plug and chug, but
Yeah.
this would be one
That
half.
I think.
You're good with that? Yep.
Yeah, I'm good with that. I think that makes sense.
Got it.
Um. Okay. This question was a little weird. I don't really understand why. I don't really know why the P shouldn't the if the direction of the wave is going up and if the wave is going this way, shouldn't the P be going up? Why is the P going down?
Wait, what did you say the direction of the wave is going where?
It says the direction of the wave is going left, right? So
Okay.
I assume that this P point would be going all the way up here. I don't
Well,
understand why it's going down though.
why if the wave is going to the left, right?
Yeah.
That means that it's gonna experience what's to the right of it.
Oh, is P the six of a fixed point? The P is not on the wave or
No, no, no. So P is only allowed to go up and down,
okay.
but the wave it's going to the left, which means that by the time that the wave this bottom part like this, by the time it reaches here, this P would go down there,
Oh, okay. Okay, I see what you're saying. Okay,
right?
that makes sense. That makes
So,
sense. Okay.
but does it at least make sense that it's not C and D?
Yeah, right, because you said it again that it's only up this point can only go up or down. It cannot go left or right.
Yeah, because a lot of people get this one wrong, and yesterday I went over it, and they said that I was saying like, okay, this is so they say that the uh P is on a dotted line, which means this, right?
Yes.
And that shows it can only move up and down. But the student was like, well, there's a dotted line here too. And I was like, good point, you know? But but yeah, yeah. So if you want like an easier way to visualize this, um you could think of it this way. If the wave is moving to the left, you can make this P part move to the right. And if it moves to the right, it will start going down like that.
Okay.
And also like let's say that you just had like a piece of paper and you just wrote like just you moved your pen up and down,
Hmm.
only up and down. And then let's say that the paper moves to the left or to the right. That
I see
thing
what you're
that you write
saying.
up and down will turn into like this type of like sine curve, right?
Yeah.
So that's another thing.
Okay. Cool. Mm.
So I saw a lot of like light things that you got wrong there. You don't have any questions?
Not quite. I mean, I think I understood the polarization why I got wrong. I don't know why I kept thinking it was like underneath the surface. But I understood that as you put on the glasses, right, it essentially like filters out the light and only specific directions of light enters. So that allows you to kind of like look through the surface.
And you have a good understanding of these terms?
Yeah, so dispersion, I thought it's like the prism. So
Yep.
as light goes through, it kind of like ducks out, and then refraction, that's the law of refraction. So as light goes at a certain angle, it kind of bends or something across the normal. That's what I kind of get. And then reflection is just like mirrors, right? So light goes in and then it reflects the other way, I guess.
Um, be careful there because when we talk about mirrors, we talk about optics, right?
Yes.
But in the context of refraction, like let's say this is N1, N2, and that N2 is larger than N1, and this is a normal line.
Okay.
We have this incident ray with angle of this will always be relative to the normal.
Hmm.
So I'm going to write, oops, angle of the incident ray. Okay. Now, this will also produce a reflection, which I'll call theta capital R. And angle of incidence is equal to angle of reflection.
Hmm.
Okay. Now, this will enter into this denser medium. What would happen to it? Would its angle move, or would it move away from the normal or towards the normal?
If this thing was to move into a higher medium, you're saying?
Yep.
Yeah, I guess, I mean, I'm guessing if it's more dense, right? Wouldn't it go underneath and it go towards like the normal here?
Yeah, it'll go towards normal.
Okay.
Good. So, okay, it seems like you know this stuff.
Yeah.
So, all right, let's move forward.
The only question was this one right here. Did I get this one wrong? Oh, yeah, I remember I got this wrong. Okay. Yeah, I'm confused because if this is a convex lens and that's supposed to be um what was it? I think that's concave is converging. So yeah, I think this should be diverging. I don't know why the image is here. Wouldn't don't diverging lens make like real images or something?
Well, so this is a converging lens.
Okay, yeah. So if it's a converging lens, yeah, yeah. So if converging, sorry about that. So if it's converging, shouldn't the image be real?
So, also in the PDF folder, I have an optics table that could be really useful to use,
Okay.
and you'll see a pattern in the type of images that you see. Um, and Yeah, so I would say definitely take a look at that because you will have an instance where the converging lens can produce a virtual image. Now, this image here is upright. So real images will be inverted
Right.
and virtual images will be upright. So we can eliminate A and B. And also, if you didn't know the upright part, you can see the dotted lines here. The dotted lines that you trace backwards also indicate virtual image.
Okay.
And also, if it's a virtual image, you can only see it if you're from the opposite side of that lens.
Okay.
So that's why it'll be from position Y.
I'm sorry, I'm still a little bit lost for some reason.
Let's say you're here and this is a mirror and this is like your reflection.
Okay.
You can only see this, and this is your virtual image here. You can only see that virtual image on the opposite side of that virtual image. Meaning you can't, if you were here, you can't see that.
Right.
Right?
That makes sense. I see what you're saying. Okay.
So, yeah.
Okay.
Mhm. Yeah, I
Sure.
would definitely take a look at the optics table when you get the chance.
Okay. Um, yeah, so I want to look at this. I don't really understand why is it not an epimer though? Because it's still only varying at one chiral center. Isn't that considered technically an epimer? So I don't really understand why it's not.
So tell me what enantiomers are, diastereomers.
Yeah, so enantiomers are essentially mirror images of each other. So that would mean that both of the molecules have like they have all chirality, but all the chiralities are essentially switched. Um
So enantiomers, opposite stereochemistry at every chiral carbon.
okay, yes, that's a better way to put it.
Got diastereomers, opposite stereochemistry at least one, but not all.
Okay.
Epimers only at one, meaning opposite stereochemistry only at one. Now, that means diastereomers can also be that, right? So the
Hmm.
real difference is that epimers are what we use for non-rings, like straight chain, like sugars, right?
Yeah, epimers are typically for sugars. Yeah, that's what I was saying.
Yeah, like but so the reason it won't be epimers is because we have a ring. If it was a straight chain, epimer can work. But since we have rings,
Hmm.
we can't call them epimers.
And same thing applies for sugars. Like sugars, we wouldn't call them. If this was like a sugar, or
Oh
yeah,
no,
this is,
I mean like so like when we think about like so this is like the C2 epimer of glucose, which is just mannose. So it's a straight chain, right?
yeah.
So that's when we can have epimers.
Okay, but in this case, like if it's in a ring again, as you said,
Yep,
no epimers. Okay.
correct.
And I got 94. Yeah. So I think I was confused with I think C and D. Um, why would it be D? Because if it's SN1, right, I think it would still form a reaction at this point too, right? So is it because this is resonance stabilized so it can hit two more points or something? Or
So SN1 reaction, what happens?
yeah, it's a two-way pathway. So um you have hopefully if you have a good leaving group, a nucleophile attacks, and you have a carbocation formation.
Well,
And
so take a step back there. So SN1 is when you have to, like the nucleophile can't just attack, it has to wait for the leaving group to leave first.
oh, right, right, right. Okay. And then the
So,
carbocation forms and then it
yeah,
attacks.
so if we have a carbocation here,
Mhm.
this can move here to stabilize that charge.
Okay.
Yep. I
And
also
compare.
have, yeah, I also have in the PDF folder an Orgo intro PDF.
Okay, I'll check it out.
Yeah.
And then compared to this, it doesn't have that
Yeah.
extra.
Because when this leaves, this is positive. Nothing is like, stabilizing this positive charge.
Okay. And
Yep.
then yeah, I think for the context of this question, like I understood it, and I was just wondering if you have anything else that I should probably try to look into more. In the context of this, like I understand why like iodohexane is a better choice for SN2 reactions. Because it's like it's a bigger molecule and it's able to stabilize the charge. Do you think that's the most I should know about recognizing like good leaving groups and whatnot, as long as as long as it's bigger and more stable?
Okay, let's see. So SN2 reaction for uh when reacting with bromide, potassium bromide. So um Forgot. Is this open up the periodic table real quick? I forgot.
Yeah, I think you're right. ClBrni. Yep.
Okay. Now, okay, if we're reacting with potassium bromide and we want that bromine to um uh to come in and replace something in one of these choices, the only thing that, you know, has a smaller, electronegativity is the iodine compared to the bromine. So,
Mm.
so yeah, for the chloroethane, the bromine is less electronegative, so that won't work. And for the anything with fluorine, that won't work either. So the only thing that will work is the iodine.
Right. So like let's say like just in regards in figuring out a good leaving group and whatnot, is that the is should I use the key of that, like as long as it's a bigger atom and as long as it's able to stabilize more charge, like that's typically what makes a good leaving group, and just leave it at that, or should I
Oh, I
be
see
more?
what you're saying. Um, let's see. Okay, a leaving group could be a weak base. So that could be like F minus, Cl minus, Br minus, I minus. Um, and then you can think about, you know, the what if whichever one has a higher electronegativity, is going to be more strongly bound to some type of molecule. So for the like yeah, for so the chloroethane here,
Yeah.
the chlorine has a stronger um affinity for the ethane here compared to the bromine. So, but the iodine is the only one that has a lower amount of electronegativity. So yeah, you can think of it as electronegativity, I suppose. Um, with
Okay.
with the leaving group being something that would be for the lower electronegativity. So
Okay.
maybe you could think of electronegativity inversely proportional to how good of a leaving group something is.
Hmm. Okay, that's a good. Okay, yeah,
Yeah.
that's a good way to put it. Okay, cool. And yeah, I think that was really it, honestly. Yeah, I don't think there's anything else besides that. Okay, yeah, I think we're done. I think it's 3:15, so.
Okay. So now that we've covered all of this stuff, um, I'm going to send an email to say to look over in the PDFs folder, um, optics table, um, Orgo intro,
Okay.
and there's another thing I think. Um,
I'm sure it was electrochem, but I mean, probably nobody around.
oh yeah, yeah, yeah.
Let me get my phone. Give me a second.
Okay. So yeah, so I think that. Oh, yeah. So, okay. So that's what we wanted to do for this week, which is finish going over all of this content stuff. Now that we've done it, um, you're ready for your practice test.
I let me stop sharing my screen for a second. I still the thing is I still have like the BB questions that I want to go over a little bit. Like I got a couple, but like obviously we can't today.
Oh,
So
BB from the.
content diagnostic, yeah.
Oh, okay. Sure, sure, sure. We
So
can
I'm
do that.
thinking obviously we can't do that today, but
Mm-hmm.
I mean, we can do it on Friday and then we'll see how that goes.
Oh yeah. Yeah, okay.
We'll see you on Friday. So
I forgot that was the plan. So, yep. So on Friday we can finish going over all of that stuff, and then yeah, you'll probably be ready for a third party uh,
okay. Yeah,
soon.
because my plan is like I'm gonna go over the I have like a couple questions left on the BB. I'm gonna go over that. Then I'm gonna kickstart on the section bank. Oh, I forgot to ask you that section bank. Should I don't time myself, right? I should just take my time trying to finish them. Okay.
Yeah, the only things that you'll be doing timed will be the practice tests.
Okay. Yeah, yeah. That's kind of nice to hear. All right, awesome. I will see you on Friday. And oh, I'll send you the cash right now. So how much is it? It's
113.
15, where are you? There you are. Okay. Yeah, I just sent it right now.
Okay.
All right, man. I will see you on Friday.
All right, awesome. Take care.